As our nation grows, our need for oil grows as well. In fact, we use nearly 700 million gallons of oil every day. That's enough oil to fill a line of 10,000-gallon capacity railroad tank cars, stretching from San Diego to San Francisco, a distance of about 400 miles. And that's just for a single day. Obviously, our present supply of oil won't last forever. So until practicable alternative energy sources can be developed, the search continues for new oil. But new wells are often drilled in very hostile environments, or farther offshore in waters deeper than ever before. As you might imagine, all these new wells are drilled at extremely great expense, with absolutely no guarantee that oil will be found. So, for a number of years, oil people have been turning their attention to old oil fields, fields that appear to have been pumped to the end of their life. For in reality, a lot of oil remains locked in the ground, because ordinary production methods, as good as they are, just cannot get all the oil out. In fact, about 2/3 of all the oil already discovered is still trapped beneath the ground. That's a lot of oil, and some of it may be recoverable. But how? Well, not easily or cheaply, that's for certain. But many companies, universities, and the federal government are devoting extra effort and a good deal of money researching ways that might work to get the oil left behind. Using data from extensive field tests, these researchers are finding some of the answers. It's here that enhanced recovery begins. This is Oil the Hard Way. You're looking at samples, called core samples, of an actual oil reservoir. As you can see, an oil reservoir is made up of solid rock. Well, maybe not so solid. Actually, a reservoir is full of small openings called pores. If oil exists in a rock, it is in these tiny pores that it occurs. The pores must be connected together so the oil can find its way through the rock and into the producing well. When the pores of a rock are connected, the rock is said to be permeable. Thus, an oil reservoir is composed of porous and permeable rock. In addition to oil, practically every oil reservoir also contains gas and water. Here, oil is shown in green, water in blue, and gas in red. Water and gas in an oil reservoir are important because they can provide the pressure necessary to drive oil out of the rock, into the well, and up to the surface. In some reservoirs, gas collects as a cap above the oil. When a well is produced, the gas expands and drives some of the oil into the well and to the surface. In other reservoirs, gas dissolved in the oil comes out of the oil to drive it to the well and up to the surface. In still other reservoirs, oil lies above the water. When production begins, the water drives the oil into the well. Many reservoirs have a combination of drive mechanisms. Both gas in or above the oil and water below act in combination to drive oil out. However, except in rare instances, the pressure in the reservoir falls as oil is produced. At some point, there will no longer be enough pressure available for the well to flow on its own. So, artificial lift, a beam pump in this case, is used to produce more oil, plus other fluids, out of the reservoir. But sooner or later, the amount of oil that can be withdrawn with artificial lift falls to a very small amount or ceases altogether. This marks the end of the first or primary phase of recovery. However, there's usually a lot of oil left behind after primary recovery, often up to 75% and sometimes even more. With this much oil still in the reservoir, you can see why enhanced recovery has stimulated the interest of oil people. If even some of it can be recovered, it will help shore up our sagging supplies. One tried and true method of enhanced recovery is water flooding. It's been in use for years. Powerful pumps are used to inject water down wells and into the reservoir. From the injection wells, water sweeps through parts of the reservoir and moves some of the oil left behind toward production wells, much like natural water drive. However, a water flood isn't perfect. For one thing, oil and water don't mix. Thus, as the water bank advances, some of the oil remains trapped in the pores and is bypassed. Also, water typically flows easier than oil. That is, water is less viscous than oil. What this means in the reservoir is that the water channels or moves on past some of the oil in the rock, leaving it trapped behind the line of scrimmage, so to speak. Overall, after water flooding, about 2/3 of the oil is left behind. That totals out to over 300 billion barrels in the United States alone. And this 300 billion barrels of oil is not recoverable if only conventional technology is applied. Why? Principally for two reasons. First, some of the oil is like this, so thick and viscous it won't flow. This type of oil can't be swept out by conventional water flooding. Second, as mentioned earlier, as oil is produced, a portion of it remains trapped in the pores and is bypassed by water. Surrounded by water, this oil is held in the pores due to forces created between oil and water when they come together. These interfluid forces are strong enough to keep oil locked in a reservoir and must somehow be overcome to recover the oil. So if this oil is to be recovered, or if this oil is to be gotten out of a reservoir, then some of the more exotic and expensive forms of enhanced recovery will be necessary. First, let's cover some of the thermal processes, methods that use heat to recover some of the more viscous oils. Of course, we can't use a hairdryer in a reservoir. So, large burners on the surface are used to make steam in boilers. The hot steam is injected into the reservoir to heat up the oil. Then, steam injection is stopped, the well closed in, and everything is allowed to soak for several days. The steam cools down, and a zone of hot water and less viscous oil forms. Then the well is reopened, and if all goes according to plan, the hot water and thinned oil are produced. This process of steam injection soaking and production can be repeated over and over and is called cyclic steam injection, or huff and puff. Another steam injection process is steam flooding. Steam is continuously injected into one well, and after a delay, fluid is continuously produced at another well. The steam is injected into the reservoir and heats up the oil to reduce its viscosity. As the steam flows through the reservoir, it cools and hot water forms. The hot water moves the thinned oil toward the production well, where oil and water are produced. Through the art of animation, we've reduced the actual time it takes from typically several months or years to mere seconds. Another way to add heat to a reservoir starts with compressed air. The air is injected down the well and into the reservoir. A heater in the well ignites the oil in the reservoir. This is called in situ combustion because in situ means in place, and combustion occurs in place in the reservoir. Air injection continues to keep the fire burning. The heat thins the oil, causes gas to come out, and changes water in the reservoir to steam. Steam, hot water, and gas drive some of the oil to the production well. Not all of the oil because of overriding, but at least some of it. All of the thermal methods attack the viscosity problem. But much of our unrecovered oil is trapped by interfluid forces between oil and water. How can these forces be attacked? Well, two methods are chemical miscible and gas miscible processes. Miscible simply means capable of mixing. For example, you might recall that oil and water won't mix. They aren't miscible. But stir in a little chemical called a surfactant, and presto, they mix beautifully. This is a chemical miscible process, and the chemical in this case is a surfactant. Similar to the way a laundry detergent works to remove dirt from clothes. A surfactant can work to help recover oil from reservoir rock. Stored in large tanks at the site, the surfactant can be applied in one of two ways. In one, a batch or slug of fluid containing surfactant is injected into the reservoir. In another, an alkaline or caustic solution is injected into the reservoir. The alkali or caustic reacts with acid in the oil and forms a surfactant in the reservoir. But whether the surfactant is injected or created in the reservoir, if all goes well, a zone of surfactant washes through part of the reservoir and breaks down the interfluid forces between oil and water. Thus, some of the oil is released from the pores and swept toward the production well. A chemical called a polymer is mixed with water. The thick water-polymer mix is injected into the well behind the surfactant and helps move the surfactant slug through the reservoir intact. Not all of the reservoir is swept, but the polymer helps. After the surfactant and polymer slugs, water is injected to keep the drive going. And after a fair amount of time has passed, and if all goes according to plan, production begins. Looks easy, but it really isn't, because an individual chemical formulation has to be developed for each reservoir. And even then, failures still occur, but research continues. This drilling rig is not drilling for oil. Instead, it's seeking another important natural resource: carbon dioxide gas, or CO2 for short. Why drill for CO2? Well, like chemical surfactants, certain gases under high pressure sometimes work to break down interfluid forces between oil and water. One of the gases that seems to work best is CO2. Further, while other CO2 sources are available, it appears that the least expensive source is in naturally occurring subsurface reservoirs, some of which are highlighted on this map. When CO2 is injected into the reservoir, there's an interchange between some of the oil molecules and some of the CO2 molecules. Thus, a zone is formed that's composed of CO2 and crude oil mixed together. This CO2 oil miscible zone breaks down some of the interfluid forces between oil and water. So as injection continues, the oil and water are moved toward the production well. One problem. CO2 is lighter than water and usually lighter than oil. So, CO2 tends to override and channel through the reservoir, leaving parts of it untouched. To help the overriding and channeling problem, sometimes CO2 injection is followed by water injection, which in turn is followed by another CO2 slug, then a water slug, then CO2, and so on in alternate slugs. The enhanced recovery methods you've just seen, simplified for clarity, are the major types that are in use today. Some are tried and true, others have been tried and have failed, and still others are being developed. But all involve the application of complex technology to the oil field. And all the methods have a common goal, that of recovering as much oil as possible. Further, it has been said that petroleum reservoirs are like people. No two of them are alike. So like a suit of clothes and a person, an enhanced recovery method must be tailored to fit a particular reservoir. Also to be taken into account in the efficient design and implementation of an enhanced recovery project are the properties of the reservoir rock, the properties of the oil, gas, and water in the rock, the amounts of oil, gas, and water, the temperature, the depth, and the pressure. And when you consider that reservoirs are buried well out of direct sight, often thousands of feet deep below the Earth's surface, it's easy to understand why it requires many experienced people to even attempt to accurately describe a reservoir and predict its behavior. So, it's no surprise that enhanced recovery projects cost a lot of money. Money to drill more wells. Money for research and development. Money for special facilities and equipment. Money for chemicals and other substances needed to get oil out of the ground. And since time is money, money to invest from the start of a project until it pays out perhaps several years later, if it pays out at all. Of course, the potential rewards are high if there's enough oil in a reservoir, and if the enhanced recovery method chosen is best for a particular reservoir. But no matter how well a project is planned, only the actual recovery of oil will tell, and that typically takes several years. The United States Department of Energy estimates that 25 to 45 billion barrels of oil can be recovered through enhanced recovery. In other words, out of a total of 300 billion barrels estimated to be in place, about 25 to 45 billion barrels may be recoverable. But this 25 to 45 billion would double, or more than double, our current remaining oil reserves. So, there's no doubt that enhanced recovery oil represents a great natural resource that we cannot afford to lose.